Hello and welcome to the latest webinar by BYK-Gardner. My name is John Kowalski. I'm part of the marketing team here and I'd like to welcome you. Today we have a special presentation kind of outside of our normal webinar series or office hour series. It is a follow-up to the National Coil Coatings Association Fall Technical Meeting. This is a bit of an extension of that presentation that will go in a little more in depth into color tolerances. Before we get to our presenter, we are recording this. So immediately following, you'll receive an automated link that will lead you to the recording. So feel free to share with colleagues, watch again later, grab screenshots, whatever you need to do. Also, if you have any questions after the fact, you can hit reply to any of the automated messages you receive, and it'll come to my team and we'll route it to the technical specialist in your area. Also, we may have some time at the end of this for a few questions. So if you do have questions, please log them in the chat box located in the bottom right-hand corner of your screen. We'll get to them time permitting. If we do run out of time, we will follow up with you individually to make sure those questions are answered. So jumping right into it, let me introduce Mr. Greg Shrider. He is our Vice President, Head of Global Key Accounts here at BYK-Gardner, and we'll be walking you through color science and digital color standards for the coil industry. Greg, how you doing, sir?
Good, thanks, John. Can you hear me okay?
You bet. All good. It is all right. Yours.
Thanks. Well, welcome. And like John said, this is a follow-up to the presentation that was given at the fall technical meeting. And just kind of an agenda, we'll go through state of the industry on color measurement for coil, some building blocks of color, emphasizing the importance of storing data so you can later come back and learn from that. We'll talk about visual evaluation and metamerism, and then we'll jump into digital color standards. And then there will be, like John said, an extended part on color tolerancing, and then just wrap up with what our recommendations and path forward will be with NCCA. So a little bit of where we're coming from. Traditionally, the coil industry has always used 45-0 geometry in North America and 60-degree gloss measurement. Currently, majority of default is using Hunter color space, Illuminate C, and 2-degree observer. Now, a little bit about further on that is the historical background is the tristimulus colorimeters were used in the very early days, and those were based on RGB filters that had a C2 response to them. Illuminate C is an average daylight. It's important to note here that there is no actual light source that is Illuminate C. So to do visual evaluations, you really can't get good correlation unless you're using something like D65. In 1964, the CIE Commission completed the 10-degree observer, and we'll talk a little bit about that later on. And they also introduced D65 as the preferred illuminate for color matching. In 1976, that same CIE organization introduced C-Lab color space and the C-Lab color equations. Now, both Hunter and C-Lab color spaces are both opponent color spaces. So you have light, dark, red, green, yellow, blue, but they are arranged differently. The equations are slightly different. On the Hunter system, you're using the square roots and cube roots for CIE. And it's important to note here that neither scale is visually uniform. Hunter is overexpanded in the blue region, while C-Lab is overexpanded in the yellow region. Now, into the building blocks of color. Whenever we observe color, we have an illuminate or something that's a light source that is illuminating a sample. So you have some type of light source, you have an object, and you have an observer. These three things are going to be combined across the spectrum from 400 to 700 nanometers, and the output of that will give you tristimulus values, which are X, capital Y, capital Z values. Those can be converted into either Hunter LAB or CLAB. Again, it's important to note what's the light source is the physical object, and the illuminant is the data table that represents that. Here we see three different spectral power distribution curves of three main light sources: D65, which is north sky daylight at noon; illuminant A, which is tungsten, so representing something very warm light source; and then F2, or any of your fluorescent light sources, will always be notated by these spikes. And the spikes represent the different phosphors that are used to coat the inside of a fluorescent tube. So it's important that you always use the same manufacturer if you're replacing your own tubes in a light booth, for example. So when we evaluate an object, we get a spectral curve, and we call that the fingerprint of the color. Here you see four different colors with all distinctly different spectral reflectance curves. So the last part of that, the building blocks of color, is going to be, how do we quantify the average observer? In 1931, they did a test called the Wright-Guild experiment, and they had red, green, and blue filters in front of light sources, and then they had a variable light source on the other side of this black partition. And the test subject, the viewer, would look at the combination of red, green, and blue, which is close to white light, but you could vary those, and then you would vary the light source on the other side to match. That gives you these curves here that represent the response of the human eye. Now, it's important to note that in the fovea, the center axis of your eye, is where your cone cells are concentrated. So that's the red, green, and blue response that we're gathering, where the rods are more located on the outside of the, further off the axis, I should say. So those two experiments, the one in 1931 and the one that was done in 1964, yielded very different results. Number one, the size of the area that you're viewing on a 2-degree observer is about the size of a dime at arm's length. 10-degree observer is more about the size of a tennis ball. The key thing that was learned here is that the 10-degree observer corresponds better with color evaluation because you're using both your cones and your rods to evaluate color. So that gets us back to where we're measuring color and saving the data. So the reason you want to do that is you can always come back to your data and you can change any of these variables. So you can change an illuminant, you can change an observer, and you'll get different or new XYZ values, which will then give you new either Hunter LAB values or CLAB values. So a little bit about visual evaluations and metamerism. So when we go through visual evaluation studies, I have solid finishes here because it's a little bit different when we're looking at effect color. But you try to find a north-facing window. Don't want to have clutter around because that can influence what you see. Samples should be physically touching. So that's very important. If there's a space between your samples, you can't resolve color differences as well as if they're touching. And you should have some type of 45 illumination angle and a perpendicular view, or like this person's looking directly onto this printed material here. The problem with this is your light source is going to be different every single day. So the way around that is to look for some type of a light booth, and most of the time light booths simulate D65. Traditionally, it was tungsten, filtered tungsten halogen. So you have a tungsten halogen light source, you have this blue filter, and that gives you a good representation of D65. You can see how close these curves are here. If you add in a bank of LEDs, you can get even better and go to a class B, from a class B to a class A light source. Fluorescent tubes can also be used, but again, you can see the spikes here. So they're going to be close to D65, but they're not going to be as accurate. Light booths are also a convenient way to check for metamerism. So metamerism is simply something matches under one light source and it doesn't match on another. So in this particular case, it's matching under D65, but under incandescent, it doesn't match. And under F2, it kind of looks like it flips a little bit the other way. The other way to look for metamerism is just to evaluate the spectral curves. If you have two samples and they cross more than 3 times, you have metamerism. Now the trick is to figure out just how much metamerism you have. So for that, we use metameric index. The metameric index equation is shown here, and you can see that between D65 and A, like we saw in the previous slide, you have quite a bit of metamerism, and then you have some between D65 and F11. Now, the rule of thumb is if you have a metameric index that's 0 to 0.5, it's still an acceptable match. Between 0.5 and 1, questionable, and then higher than 1 is telltale sign that you really should be starting to reformulate. Now, the paint people do this all the time. They're constantly watching for this, and it's during times when you have to do pigment substitutions or any type of raw material overhaul where you really have to look at the formulation and then evaluate those spectral curves closely to make sure that you don't have metamerism. Also, following visual guidelines, here you see several different international standards. They all are using D65 as the primary illuminant. Secondary and tertiary illuminants are mentioned here, A and F2 or F11. Usually you want to get 2 dramatically different light sources. So a daylight source and usually incandescent or horizon light can be used to give you the extreme differences there to see if you have metamerism. The other thing to pay attention to, if you're not using a light booth and you're using like an overhead luminaire or a room that's dedicated to evaluating color, is the walls should be painted a neutral gray. And there's different specs here. But usually N7 is a popular notation. That's a Munsell gray that's specified. So a little bit of, I won't say test, but an evaluation is if you look at the red squares on different backgrounds, they all look different, as well as the green squares. And you probably know when you remove the background colors, they're all going to, the squares look exactly the same. So again, it's just a note to make sure that you're not also wearing like bright blue lab coats when you're evaluating color. You usually want to use a gray or a white lab coat just so any of your clothing is not reflecting back onto the samples. So on to digital color standards. So for fun, I typed in what is a digital color standard, and Perplexity AI gave a really nice, precise answer to that. I won't read this all to you, but I'll just bring your attention to 2 things. Number one, it also said color identified by name and underlying spectral data, its fingerprint. And then the other important part for using digital standards is that digital color standards don't fade or degrade over time. And we all know that when we get physical standards, we stack them up, they get scratched, they get dirty over time, and then they have to be replaced. So by going to digital standards, you're always going to be targeting the exact same target, the same spectral curve, the exact same spot and color space, and it makes it easier for everybody involved. Definition of a digital color standard is really anything that's been measured and stored to be later recalled for comparison to. So this is something that we've been doing for a long time. So it's not new. What is new is now those digital standards can be shared. And the reason for that is the tight inter-instrument agreement that can be utilized now. Previously, it was not available. So the digital standard process, typically what goes on, you have a number of master panels that were prepared. Make sure they're visually evaluated for any scratches, and they're all in good condition. You measure all of those, and you find the one standard that is closest to the average. That is your digital standard, and that should be stored in a refrigerator or a freezer or a cool, dark place, and really not to be used for anything in case you do have to remaster. Then you can always go back to the original. All the remaining standards are then labeled with LAB offsets to that master standard. The first thing that gets done is pull out a group of secondary standards and audit standards. And a typical tolerance for these are plus or minus 0.05. So very, very tight. And if you look at those tolerances for LA and B, it's a 0.09 delta E. The next thing is to find your working and visual standards. So for those, the tolerance gets opened up. And then you can distribute those, and then we start looking at line tolerances. So here we have various line tolerances that could be in play in any given production setting. Now, digital standards are also possible because of excellent inter-instrument agreement. So here you have 8 spectral curves from 8 different instruments on the same standard, and you can see that they overlay each other perfectly. And that's what you would want and what we would expect to see for inter-instrument agreement. This is the data that's associated with that. So real life data, you can see sample 5 was out a little bit more than the others. Now these were all single point measurements, not using a jig, so not guaranteeing that we were in the same spot. So there might be some differences just within the sampling set. The other thing that really drives digital standards and the use of them is excellent temperature management. And what we see here is a test that was done many years ago with a high-end benchtop and a portable with a spec of 0.2. The process was that the 2 instruments were calibrated, and the BCRA tiles were measured at 75 degrees Fahrenheit. We maintained the temperature. This was a third party that did this test. The 75-degree tiles were maintained, and then dropped the temperature and let the instruments come down to 65 degrees ambient temperature, so overnight, and then re-measure the 75-degree tiles, and then again next day back to 70 degrees, and then to 80 degrees. And what we see is the calculated mean deviation across all temperatures, and for the benchtop it was 5.46 on a delta E scale, and for the portable it was 0.26. Again, real life single point measurements, no jig involved, but seeing how that temperature control can really impact the accuracy of an instrument. Here you see inter-instrument agreement for 400 units, and you can see that all of them are below 0.1, so a delta E specification of 58.1 for inter-instrument agreement is well maintained. Again, the power of the digital standards, everybody's shooting for the exact same target. So you can see on the left with various targets, various standards measured on different instruments and different plants, and the impact of everybody going to the exact same target with really good inter-instrument agreement. Now everybody's shooting for the exact same target, and your overall production variation should be much, much less. Okay, on to color space and color tolerancing. With either Hunter or C-Lab system, you can navigate a couple of different ways. You can use LAB tolerances or attributes. So in this case, you come out, you find your level of lightness, darkness. So in this case, 58.12. Then I come out on my red axis, 38 or 36.41. And then in the positive direction for yellow, 24.26. That's where that orange lives in color space. With the C-Lab system, you can also navigate using polar coordinates. So again, the same level of lightness, darkness, but now I'm going to come out on my hue angle, and I'm going to start at 0 or at A, and it's counterclockwise. So I'm going to go, in this case, 38 degrees, and I'm going to draw a vector from the center of color space out to 44.32. And that's the same exact space, but I'm just navigating using polar coordinates instead of Cartesian coordinate system. One thing that's a little bit different when we do calculate the hue difference, we call delta H, it's this distance with the same amount of chroma. So even though my standard's further out here, I have equal chroma, and I just take this distance here. So both with Hunter LAB and C-Lab, a lot of people like to use delta E as a single attribute to track. And you can see in this case, my differences between my standard and my sample, I have this difference in A, this difference in B, and then this difference in L. So three-dimensionally, this vector here is delta E. And it's an easy number to track, but you have to remember it doesn't give you any color direction. So you could be a 0.75 and you don't know if you're lighter, darker, redder, greener, yellower, or bluer. So hopefully everybody would agree that comparing sample 1 to the standard and sample 2 to the standard, that sample 1 is a closer match. It's closer because all of my color differences equally spread out across the 3 different attributes of L, A, and B. On sample 2, all of my color differences in my A value. So A is red and green. Since I'm looking at a blue, that's a hue shift. So all of my differences in hue, and important to note here is the first thing that we see in color differences are hue changes. The next thing we're sensitive to is chroma changes, and the last thing that we're sensitive to is lightness, darkness. With that said, we're also sensitive to color differences in different areas of color space. Here you can see these ellipses, and these ellipses all represent 1 unit of color difference in oranges, and in yellows, and in greens, and in blues. They're all different sizes, and they're different sizes and shapes as you go from an achromatic or a neutral color to a saturated color. And that's one of the changes, or one of the things that makes color differences sometimes hard to communicate, because as you navigate through color space, that size and shape of those ellipses are all 1 unit in this case, but they take on these different sizes and shapes. So 1 unit of color difference on a yellow is going to be larger and bigger than, say, something that's neutral and lower in chroma and lightness darkness. Here we have the prismatic display number 2, and I have to give props to David Kowalski for helping me out and giving me some good high-res images. So these are just 3 of the colors out of the book, and what we're looking at is 1 unit of color difference on top, so our standards in the center, and then you have a lighter, darker, redder, greener, yellower, and bluer sample, all of 1 unit. And then below, we have 5 units of color difference. So as we take a closer look, you can see here, it's a little bit of an eye chart, but 5 units of color difference for each of the swatches represents approximately 6 units in the CMC color space. And I'll talk a little bit about that in a couple of slides and how important that is. But all of these are all hue shifts. So they should be close to one another because it's a neutral color. The CMC value for the lighter and darker, since we're least sensitive to those differences, that's 1.5 and 1.4 respectively. So again, we see hue first, chroma, then lightness, darkness. If we look at the blue, this is a great example, again, of how the different swatches look. And if we look at the red, green, these are hue shifts, and they're up around 7 and 6 respectively for CMC, and 5 units on the A scale for Hunter. However, when we look at the yellow and blue, this CMC value drops in half to 3 units and down from 7.1 to 4.2. And the reason for that is this is a chroma change. So we're not as sensitive to chroma changes as we are to hue changes. So the top 2 represent hue changes. These 2 represent chroma change. And then lightness, darkness differences with a value of 3 on a CMC scale. So as mentioned, the CIE came out with the CIE color space and LAB equations in 1976. And since then, there's been a lot of work done to have that delta E calculation become closer and closer to how we actually view and judge color. So delta E CMC came out in the 80s using textile samples. In the mid-90s, there were paint samples added to that sample set, as well as additional samples for DE 2000. So what are some of the differences? So first, we'll break down kind of where the industry's at right now using LAB. And in tolerancing terms, it doesn't matter if you're talking C-Lab or Hunter LAB, the tolerancing system works the exact same way. And you have a 3-dimensional box. Now what happens with this box, if each of my attributes is 1, this area, this vector here is 1, that means this vector to the corner is 1.5, as shown over here. And then to go to the further 3-dimensional vector to the upper corner, then that vector is going to be 1.7. So what happens when we start to break that down is if we want to use a delta E calculation, then that single vector will lose the corners of the box. So you can either do LAB box tolerances, or you can do a delta E tolerance, which will use that single vector. And you see here, left is the sphere or the green part of your tolerance. And again, going back to some of those examples for the line, if I had a plus or minus LAB values of 0.5, then my delta E calculation is going to be 0.87. If I'm doing 0.75 for each attribute, it jumps up to 1.3. This gives you that ability to monitor and control using one attribute, but we want to try to take advantage of some of the newer equations that better closely align with how we see things visually. So what you see here is an example where we have our product standard in the center, and then we have all of these white bubbles, if you will, represent visually acceptable color match, and then the ones with the X's are the ones that visually fail or are rejected. So the box tolerance in this case closely represents what we see visually, which would be the circular or spherical tolerance in three-dimensional color space. And this is fairly accurate for achromatic or neutral colors. Where this starts to challenge is when we get into more saturated colors with higher chroma. In that case, you start to see this elliptical formation come true. So here, if I have to have a box tolerance that incorporates everything, I'm going to have this bigger box, and I'm going to be producing product in this area or in here that visually is not going to be acceptable. So what happens is then you have a box tolerance that you have to put inside the ellipse. Now I'm rejecting these numerically, but yet they're visually acceptable. So we want to try to work towards optimizing that. Reality is, right now, if you snapshot the coil industry as a whole, production lines are running to this kind of a tolerance. Paint batches are controlled to a much smaller tolerance. So the idea is if we can gather a bunch of data and we can do visual studies over time, can we prove this out to where we could expand and use larger tolerances that better correlate with visual, but still give you good color match? And it would, if we were able to prove that out, then the output for production lines could be much higher. So we want to continue to evolve. We want to continue to align with these newer equations and take advantage of them. So let's take a little bit deeper dive into how these ellipses are formed and controlled. The first one is the CMC ellipse, and you see the equation here. It's usually written this way. It says delta E CMC, L to C. That's the ratio of the lightness vector, this vector here, to the chroma vector here. And traditionally with the textile samples, that was always 2-to-1. And if people are familiar with textiles, textiles tend to have a nap or directionality to them. And that was the main driver most of the time for that 2-to-1 ratio. And again, we see lightness, darkness after hue and chroma changes. So you're always going to have a longer axis here in your ellipse to a shorter axis here for chroma or hue. So delta E94 comes around, and what are they, these added K factors, or the S sub L, F sub C, which is for chroma, and S sub H for hue. This equation corrects for the influence of chroma. So as we increase in chroma, the visual perception decreases for chroma and hue. There's no extra lightness correction in the delta E94 equation. How does that look in terms of what you would see? So again, a little bit of an eye chart, but these two different yellow samples failing on a delta E calculation of 3.06 and 2.89. When we apply 94 to it, we have sample over here and a sample right here inside. And the one inside is a 0.72 delta E94, and the one that's just outside is a 1.19. So what that means, these are weighted color differences. So it means I'm at 19%, 119% of my overall tolerance. And so you can see it's out in the hue and it's outside of the red tolerance. 0.72 means I've used up 72% of my tolerance in my ellipse. So if I'm looking at an ellipse, I'm getting close to the 75% area. So again, we can see that the scaling factor for chroma agrees better with visual and knocks down that number, the chroma value. And you can see here the scaling factors are quite large, 5.32 and 2.44. Why? Because it's a very saturated yellow. Now we jump into delta E2000. So what are we changing here? Now we're adding this G factor, and this G factor is squeezing the tolerance or modifying the A-axis. So it won't be a spherical ellipse for the neutral colors. It's going to get squeezed some. And you can see the maximum impact it would have is 0.5. And as you increase in chroma, go out to beyond 40, it comes down to virtually very, very little. So again, low chroma, G increases compared to A star and up to a max of 50%. And higher chroma, the A prime or the A value will be similar to A star in the normal C-Lab equation. So here we see, again, these scaling factors coming down from 5.32 to 2.44. Similar results for chroma. We have very similar delta E values. So chroma differences aren't impacted there. Where I have a difference for hue, then I start to pick up larger delta E's and I'm outside my tolerance. The other thing that is shown here is how it affects that squeezing of the ellipse. So it actually becomes more critical when you're dealing with neutral colors. So this is a gray, 94, it passes both of those samples. Now it fails both of those samples. Again, due to the squeezing of the A-axis. And again, it's all to correlate better with visual perception. The other thing that happens with delta E2000 is in the blue region, only in the blue region of color space. They found that for better visual correlation, these ellipses get tilted. And it's actually tilted by 24 degrees. So again, originally passing, now both of these two samples would fail. So it's gotten squeezed the ellipse again, but it's tilted is the key. So these last samples are to show you what happens as we step through different areas of color space. So what we have here is we have a target, actually some measurements done on various instruments. This green circle here is the 0.1 tolerance for delta E94. The blue is a 0.2 tolerance on C-Lab. And then we go to the gray, which is 0.3 delta E94, and then 1.0 delta E94 with the red. So this is a pale gray. We'd expect to see spheres here because it's a neutral color. If we jump to a mid-gray, almost the exact same picture, a little bit different. If you pay attention to some of the axis here, when we go to a difference gray, now going a little bit further out beyond the 1 unit here. But again, neutral color, so it's closely impacted. Now we jump to a dark gray, again, back to kind of a 1 unit axis. And then we start to look at different colors. So here, again, you have a 0.1 ellipse, and then you have a 0.2 circle for C-Lab, 0.3, 1 unit. And you can see this axis here is 1.5, and this axis here is a little over 2 units. Same thing for red. Start to see the ellipse get a little longer because it's more saturated in color, which is what we'd expect. But again, I want to point out that now my 0.1 ellipse is all encompassing the 0.2 tolerance. So you could, if you went to a delta E calculation, you would have more room with 0.1 than you do with 0.2 on delta E C-Lab. And again, C-Lab and Hunter are very close, but they are organized slightly different. So in the blues and the yellows, they flip-flop on how sensitive they are. So this is an orange. Again, we see really good inter-instrument agreement, which is showing the measurements for lightness darkness here, and in the still well within the 0.1 tolerance for delta E94. Then we have a yellow. Again, pay attention to these axes. Now we're almost up to 5 units on the chroma axis. And a green. Again, really tight control for different instruments measuring the sample. But here your 0.1 and your 0.2 delta E star are really close together. And then the different screen in the BCRE tile set. Cyan, again, well within the 0.1 tolerance, and then dark blue. And you can see here, this is going along the chroma axis here. And the hue axis would be kind of this way. So, recommendations and path forward. Our plan is to continue to work with the technical committee. We've identified some training and education opportunities, and we're implementing many of those in the field. Really want to stress the importance of saving your measurement data. You can learn a lot from previous runs, both in the paint lab as well as online, and you can do a lot of dissecting of that measurement data for learning and trialing other delta E calculations. So that'll help in exploring new color equations, and then proactively start to look at same type of measurement processes, but for metallic and effect colors. That part of the color palette is growing, and there are ways to control those online and in the paint lab, and look for future work in that area also. So I'd like to thank you for your attention, and if we have some few minutes, be glad to answer any questions.
Thanks, Greg. Yeah, if anyone has some questions, just drop it in the chat here. We have a few minutes left. It's really important work you're helping out with, Greg, and part of this committee. Are there? I'm just kind of overwhelmed by the amount of information, the detail. This has been a really great presentation. where should someone start if they do have questions? I know they can reach out to us. We can review samples and provide best practices. Your thoughts on that, Greg?
Well, I think it's like anything that you're working on. If you're in the coder world, always reach out to your paint suppliers. They're a wealth of information, and they've got a ton of samples, so they know a lot about areas of color space that are challenging and areas that are maybe not so challenging, but also what they've seen over time, and that's always a good place to start.
Perfect. And like I said, feel free to reach out to us if you need any help. Hit reply to any of the marketing messages you see. In terms, and maybe you can't divulge this information, but in terms of the NCCA and the technical committee moving forward, let me just go back to your last slide here. Ongoing work. How large of a committee is made of this? Or I guess how large of a board or committee?
The technical committee is rather large, but it involves a lot of different people. And then what comes out of that are projects or areas of focus. And that's where you get a smaller number of people in a working group to work through some of the challenges or some of the opportunities. So you can always volunteer. David Kowalski is the technical director, and he's a great source of information, as well as a really good source to connect people. And a lot of times it's just about making a connection where you can have a conversation about something and have some members help each other out.
Yeah, that's great. That's really great. The true power of the NCCA is working together to advance the industry in a whole. So
and they've got toolkits on a number of things. Not just color and gloss related, but any type of physical property testing that's common in the industry. There's toolkits for all of that stuff. So it's a wealth of information and great resource.
Great. Other questions out there, folks? Quiet group today, and that's okay. It's a lot to digest. Like I said, you'll get a link with the recording of this immediately following. Feel free to watch it later, grab some screenshots of some of the details that Greg reviewed, share it with colleagues. You can always reach out to us as well, for questions, or, like Red mentioned, other NCCA members or Dave Kowalski. In addition, give it a minute here. I think we see one question. Someone's typing, so give me a minute. Any other words you want to say, Greg? Well, we're waiting for this last question.
No, I think one of the things is if you have a challenging color, or you have any types of challenges in and around color measurement or appearance measurement, we're always available to come on site. Sometimes it's just getting eyes on a particular struggle that we can walk in, and we've seen a lot, so we can pull from previous experiences and usually come to a conclusion pretty quickly on what the issue is. Yeah. And I will say one thing that was interesting recently. We did see some fluorescence pop up when we were comparing a coil product to a plastic product that it went up against. And the plastic product had some fluorescence in it. And luckily the color 2 view that was being used is able to quantify that fluorescence as well as color. So it really helped to determine very quickly what the differences were.
Nice. Very nice. Question here. You mentioned the wall color around a light booth. Are there requirements regarding the position of the luminaries in that? And is that something, BYK-Gardner can help with?
Yes, there is a specification in automotive that a lot of people follow, and it has the luminaires at a certain angle, and then you can build a table that's at another angle, and that's all specified. So we have that specification. I don't have it in front of me, but we can share that. It's not confidential or anything. And then if you're using the luminaire like in a ceiling or overhead flat, then there are some recommended number of luminaires that you would put in a certain size room, and we have those specifications also.
Nice. Okay. Yeah. So if anyone would like that, just hit reply or drop your name in the chat here, and we can get that to you. All right. Well, thank you, Greg. A lot of great information you shared in a short amount of time, so we really appreciate your time and expertise here. Thank you, everyone, for attending. Like I said, you'll get the recording. If you have any questions after the fact, hit reply. It'll come to the marketing team here, and we'll route it to Greg or the technical expert in your region. Thank you, Greg. Appreciate the time. And we look forward to seeing you on future BYK-Gardner web seminars. Have a great rest of your day.
Take care.